In this lecture, we will consider failure theories, and in particular how the theories can relate to brittle and ductile materials. So as a quick review, last time we spoke of the maximum distortion energy, the von Mises theory, and we looked how the application of this theory matches facts very well for ductile material. We also talked about, we just mentioned in passing, that the maximum normal stress theory appears to work well for brittle materials. And we talked about this maximum shear stress theory, and that it seems to be conservative. And today we're going to look and see how it relates with the maximum distortion energy theory. So first, the distortion energy for a 2D case traces an ellipse that's the boundary of failure and not failure. So this ellipse is the boundary. If I have a stress condition in which my principal stresses cause the part to reside in this outside region, then we'll say that it's going to fail. And if it's on the internal region, then we're going to say it's not going to fail. And therefore, our yield strength is related to the two principal stresses that are non-zero. I call them A and B. So if we consider the first point, this point here, where sigma A would be what we would call our greatest principal stress, and the other two principal stresses are zero, this is the actual test that's probably performed to get the data. If we get the data here, then we can graph our first point of the ellipse. The next region of the ellipse is when sigma B is a principal stress, but is less than sigma A. So sigma A is still our highest principal stress. This top region now, sigma B, is the highest principal stress. So if you think about it, there's really just a reflection. If I call sigma A sigma B and sigma B sigma A, then my graph would just revert around this axis, and these are really expressing the same fact. When I get to this other point, sigma B is the only one that exists, and now sigma A is equal to 0. Quadrant 2 represents where sigma B is positive and sigma A is negative. So I have a state in which there is some compression and some tension, and remember sigma C that's not shown is equal to 0. This case is the case where it's a uniaxial stress, but it's in pure compression. And in this case, sigma A is in compression and sigma B is in compression, but A is in more compression than B, and B is in more compression than A. And then pure compression, where sigma A is the only principal stress not zero, and it's in pure compression. And then finally, very similar to this upper region here, sigma A is positive and sigma B is in compression. So that's the distortion energy theory. And again, for a given stress case, for my given loading conditions, sigma A and sigma B would be in one of these categories around this ellipse. And what I'm going to do is I'm going to find my sigma A and sigma B and see how close it is to the maximum it could be as defined by this equation, this elliptical equation for the yield stress. The maximum normal, which we said would be valid for brittle materials, has a different criteria. It doesn't consider shear stress at all, and as such, all it does is it takes the maximum stress. So if it's in tension and sigma 1 is greater, the greatest value, so for instance in this region right here, sigma A is equal to the highest principal stress, and in this region, sigma B is equal to the highest principal stress. So it's the maximum. And if we're in compression, then down here we would look at what's happening in compression, and all we would consider is whether sigma 3 is bigger than the maximum compressive yield strength or ultimate strength. Now, notice the difference in the two theories. On the one hand, the maximum normal theory is conservative relative to the distortion energy in this regime here, but the distortion energy is more conservative in this regime. And this is why it's so important to actually do tests, because what we'll find is that brittle material fails a long time before the maximum normal theory, ductile materials fail a long time before the maximum normal theory says they ought to fail in this region. Our third theory is the maximum shear, and if you notice its points, for the actual points where we test, for uniaxial testing, it matches identically with what we would find with the distortion energy theory and with the maximum normal theory. So you can imagine how these all came about. People did tests and they have this data point and this data point and this data point and this data point. And now they're trying to figure out with all of those data points, how do you fill in the gaps for other stress conditions that they don't want to test every time. This one's condition is to say that it's the shear stress that actually causes the problem, tau max. And tau max is defined as the highest principal minus the lowest principal divided by 2. And so this is the regions that result from that. In this region, the lowest principal is 0 because they're both positive. In this region, the lowest principal is sigma A because it's negative, and the highest principal is sigma B because it's positive. If I were to draw a line from minus 1, 1 times the yield strength to 1 minus 1 times the yield strength. So this orange line drawn here on the graph, this represents pure shear loading conditions. And so the three theories have three very different results for what the yield stress in shear ought to be. So let's look at them. The von Mises we derived, and we said that the shear stress, the shear yield stress, is 1 over the square root of 3 times the normal yield stress, or 0.577. For the maximum shear, we would see that the yield stress for shear is equal to the yield stress for the normal load. And then for the third case, for the maximum shear condition, we would see that the yield stress in shear is equal to 1/2 the yield stress. And you can see that this is conservative compared to the von Mises. Here's some graphs of actual materials that were tested. These materials up here are ductile materials, and the gray cast iron down here is a brittle material. And you can see that the brittle material went a lot further than the von Mises predicted it ought to, and that it appears that the maximum normal is doing a relatively good job of predicting how it's going to fail. On the other hand, the ductile materials really seem to follow the von Mises better than any other theory. So the results after many years of testing is that if a material is ductile, homogeneous, isentropic, and even, and if it's loaded in static conditions, then the failure evaluation we ought to use is the distortion energy, or the von Mises theory, with a caveat that if you would like to use the maximum shear, that's considered acceptable because it's more conservative than the von Mises. It's very important. If the material is ductile, you cannot use the maximum normal stress theory because it is not a good predictor for some cases for ductile materials. And then as a definition, even materials are when the compressive strength is equal to the tensile strength. So let's consider a material that's been tested twice. First, it was tested in a tensile test and uniaxial tension, and it was tested until it failed. And so here's the Mohr circle for the tensile test. And then the project was repeated, and this time it was put in compression, and here's the Mohr circle for how the compression test went. This would be an even material because the ultimate compressive strength is equal to the negative of the ultimate tensile strength, and the maximum shear that the material can handle is roughly a constant across those two lines. For uneven material, however, the tensile test has very different results than the compressive test, because the ultimate compressive strength is much greater than the tensile strength, and that's typically the case. Typically, if a material is uneven, it handles compression better than it handles tension. A good example is concrete. You can put as much weight as you want on it in compression, but you can't put a lot of weight on it in tension. Notice that the maximum shear for the two of them is no longer a constant between the two, but it is some sloping line that has to do with how different the ultimate tensile strength and the ultimate compressive strength are from each other. In general, we say that ductile materials are even, and in general, we say cast materials and brittle materials and composite materials are often uneven. So one more note about ductile versus brittle and the way they fail and the mechanism of failure. If you remember from these pictures earlier, the ductile material yields before they fracture, so we see the yield line, and when it yields, there's roughly a 45-degree plane, which indicates shear effect. And if you think about the whole, even the definition of the distortion energy, it has to do with not the change in volume, but with the distortion in shape, which is affected by the shear that's happening to the element. So it makes sense that the shear is what causes failure in ductile materials. For brittle materials, in tension, they fail across the normal line, which does indicate that the maximum normal theory is a good indicator for when this will fail. When brittle materials fail in compression, there seems to be a combination of shear and moment effects. And so we need to do a little bit of refining of our theories for brittle materials. So taking the maximum shear theory and the maximum normal theory and then modifying the two of them to kind of combine them together, that's what Coulomb and Moore did. It's called the Coulomb-Moore theory, and it was modified again, so we were left with the modified Moore theory. And again, this is sigma A and sigma B. You have your ultimate tensile strength, so this point right here was tested, and this point was also tested. And then probably it was put in a compression test, and this point was graphed. So we're relatively confident about this point here and this point here. And again, the same points on the sigma B axis. What the next slide is going to show is a zoomed in portion of this region, quadrants 1 and 4. So let's take a look at those in a little bit more detail. So, as best as we can understand, the modified Moore theory is the best theory for uneven, brittle materials that are in static loading. And if you notice, there are several different regions. In this first region, A, the way we're going to define our factor of safety is we're going to say that the ultimate strength is divided by wherever I'm at, wherever my sigma A is. So that's going to be my factor of safety. As it's drawn in the diagram, it looks like the factor of safety for this loading condition is about 2, because this point is roughly halfway out there to the ultimate. For region B, we're going to say that it's the same scenario, but we got to the scenario a different way. Recognize in case A, this is when both of my principal stresses that are non-zero are greater than 0. For case B, one of the stresses is less than 0, but the one that's less than 0 is closer to 0 than the one that's greater than 0. For case C, compression is dominating now, so the one that's less than 0 is further from 0 than the one that's greater than 0. And now I have a more complicated factor of safety equation that includes the tensile and the compressive, and it includes both principal stresses. And finally, if we're not shown, I have in here quadrant 4, it's quadrant 3, as we normally think about the quadrants on a graph. And that shows if it's in pure compression, then our factor of safety now becomes a pure compression. Only depends on the ultimate compression strength and the stress that's in compression, the highest stress that's in compression. So what if I expand this now to 3D? Well, the way to do it, instead of walking through the analysis and doing a graphical analysis, we'll do it with equations this time. And now we just say that if the principal stress, the highest principal stress is greater than 0, then we're going to find 7 different values. We're going to calculate C1, C2, and C3. And then we're going to compare, and we're going to take the maximum value of these C1, C2, C3s that we calculate, sigma 1, sigma 2, sigma 3, and 0. Whichever one of these values is the highest will be plugged into the ultimate tensile divided by that stress level, and that'll give me my factor of safety. If the part is in pure compression, then I'll use this one. This is the equivalent stress, the von Mises equivalent stress, and I'll use the ultimate compressive strength and divide it by this equivalent stress. So here's some empirical data that demonstrates that the modified Moore theory does indeed demonstrate best how things behave for brittle, uneven material.